Hey, you, polymer chemist, protein researcher, or macromolecule specialist. And yes, small molecule expert, even though you might be slightly lost at SCM, I think that this paper could still be something for you. Do you recognize or experience any of the following problems when working with liquid chromatography? Do you fear complex distributions? Are you tired of long days, weeks, or even months trying to optimize your LC method? And are you sometimes agreeing on a suboptimal method because you cannot afford more time, costs, or headspace to optimize it even further? And don't you just sometimes wish that you could analyze your big molecules with GC because it sounds so much more easy? Then I think that retention modeling is the solution to your problem. Now, there might be several things going through your mind right now. For example, retention modeling, what is that? We do real chromatography, not the one in a computer. Or you might think, yeah, of course retention modeling is an option, but that all that research is only performed on easy and small molecules, and my big analytes outsmart those for sure. We understand that you might see it like that, and we understand that finding your way through the retention modeling forest is not as easy as it should. But we have very good news. We agreed with you to such an extent that we decided to organize it for you. That resulted in a review this autumn entitled Recent Applications of Retention Modeling in Liquid Chromatography, where we bundle several approaches of retention modeling. This resulted in our master scheme, which I will guide you through right now. The first part is method optimization, where we start from a very badly separated sample and try to optimize it to great separation with retention modeling. In the second approach, we look at method transfer, where we try to get similar separations on different systems. In the third part, we look at column characterization, where we use retention modeling to characterize the dominant retention mechanism and compare columns. In the fourth approach, we look at the more extreme science performed in retention modeling and try to get a deeper understanding of what retention is. In the fifth approach, we look at lipophilicity determination, where we use retention parameters to say something about the analyte's polarity. As you could see in our master scheme, all of these approaches use some kind of scanning experiment, which is something we discuss more elaborately in the review. To be more specific, if you're more from the life sciences side, then go check out our Understanding Retention and our method optimization part, where we discuss retention modeling performed on peptides and proteins. If this is nothing for you and you're more from the synthetic polymer side, then go check out our column characterization and comparison part, where we discuss the use of polymers as stationary phases or their ability to separate them and relating that to end group selectivity. We end the review with some key conclusions and some concrete recommendations for you as a user. And are you now getting curious whether retention modeling has reached a level where it can be helpful to you and help you with your day-to-day struggles in the lab? Then go check out our review in the link below, and we hope to see you there. Bye!